Good morning and welcome to this webinar brought to you by DNV Software on the subject Consequence Modeling and Quantitative Risk Assessment. Thank you for taking time to listen in. The presenters for today are Colin Hickey, Head of Department Risk and Reliability, and myself, Sive Manuelsen, Regional Sales Manager, Risk and Reliability. Here is the agenda for today. We will shortly introduce DNV, and Colin Hickey will take you through the loss prevention landscape, the next generation consequence modeling technologies in Fast, performing a QRA using Safeti, and occupied building analysis with Safeti 3D explosion modeling. We will wrap up the session with a Q&A, and the whole session will last for 1 hour 30 minutes. I'll start up with a short introduction to DNV. DNV help manage risk through a very broad service portfolio, but we have 3 core services: classification, certification, and verification. DNV has more than 10,000 employees in close to 300 offices in about 100 countries. We want to stand out by being a trusted and highly competent partner of to our customers. That is why we keep a very high level of highly educated staff. DNV is an independent foundation with a solid financial background. No single majority group can have control of the foundation. DNV's broad experience in the oil and gas industry extends across oil and gas operating companies in the upstream and downstream sectors, pipeline transport companies, subcontractors, suppliers, authorities, and investors. 65% of the world's offshore pipelines are designed and installed to DNV's pipeline standard, while as 40% of the world's floating production, storage and offloading vessels are built to DNV class, and 30% of the world's LNG terminal projects are supported by DNV. Due to our technology experience, knowledge sharing philosophy, and the trust we enjoy from both the industry and authorities, we manage a number of joint industry projects to ensure new standards and innovation are developed for the good of all stakeholders. DNV Software. We are an independent business unit within DNV. We are a supplier of commercialized software products with more than 50 years of experience in developing software. DNV Software has more than 300 employees working from 10 offices around the world, where 3 of these are development centers. The new risk reality is a statement that illustrates the increased complexity of society. And to be able to deliver on these demands, software is one of the factors that will help you on your journey. DNV Software is a leading provider of software for managing risk in energy, process, and maritime industry, offering solutions for design, engineering, strength assessment, risk and reliability, QHSE, risk, and asset integrity management. DNV Software offers 7 leading brands within strength at sea, risk and reliability, safety and integrity. They all share the same DNV Software brand values: complete solution, most user-friendly, most value for money, and professional service. Our focus area for this webinar is within risk and reliability and the products Fast and Safeti. Here are some of our clients. That was a short introduction to DNV. I will now hand over to Colin Hickey, who will take you through the rest of the agenda.
My name's Colin Hickey, and I'll be taking you through the next few slides. So we'll start by trying to place Fast and Safeti and their capabilities into the world of loss prevention. So the job that safety engineers have to carry out to try and manage major accident hazards. So here we have a diagram produced by the UK Health and Safety Executive, and it does a very nice job of trying to illustrate all of the activities that an organisation carries out to try and manage major accident hazards. So major accident hazards are a certain class of accident that have a high level of effect, and these may arise from the basic underlying hazards of the properties of the plant. Either there's toxic substances or flammable substances, or things are at very high pressure or temperature and things like that. There's also other areas, so infectious materials and things, that's also of concern to the HSE. The main area that Phast and Safeti fit into this process is in trying to predict the outcome of loss of control. So here in this large picture we have this process along the bottom of trying to work out what accidents can happen. So you start with your hazards, you think about how you can lose containment, so through corrosion or operator error, so things like overfilling, high pressures and high temperatures having an effect on the integrity of equipment. And then you come up with your loss of containment scenarios, and on those you perform consequence analysis. And consequence analysis will give you an idea of what happens if a flammable material or a toxic material gets out into the atmosphere. So what level of radiation or toxic dose will you experience? An analyst also has to consider the likelihood that these events occur. So consequence alone is not always that useful in trying to determine which are the most important accidents you have to manage. So where should you direct your efforts? So probability is also a concern here, and risk assessment is the job that Safeti can help you with. So Phast is the consequence engine of Safeti, and that will help you with consequence analysis. You put in a number of other factors, and that will help you perform a risk assessment. Now the risk assessment is a very useful overarching measure of what level of risk your facility or your organisation presents to society. But to help you manage that risk, a very, very key aspect of this is the risk profile. So comparing the risks across your site and thinking about where those risks come from and what they impact. And it will help you organise the criticality of the hazards present on your site so that you can focus your efforts on the most important and the most cost effective. So that's really the core of where Phast and Safeti fit down here, just looking at major accident hazards and trying to simulate what happens when these losses of containment occur. Now, as you gain more experience of using Phast and Safeti, you realise that it's a large, complex suite of models that are all linked together. But you actually have a lot of manual control over these linked models, and you can use them independently. So you can put in your own discharge terms. So rather than relying on Phast to work out how much material comes out if you experience a corrosion crack or a line rupture, you can actually define your own source terms and feed those manually into the dispersion calculations. So this principle exists with the effect models as well. So the flammable, toxic and explosive effects models, you can look at particular scenarios. You don't have to rely on discharge, dispersion and pool calculations preceding any analysis of a fireball or a jet fire or a pool fire. You can look at the effects in detail. So with that in mind, knowing that you have this full control over this modelling suite, you can do more sophisticated analysis to try and think about preventative and mitigating barriers, and this is an important part of major hazard management. So organisations will have in place preventive barriers, so operating instructions, mechanical equipment interlocks, things like that, to try and prevent loss of control. Once you have had a loss of control, some kind of loss of containment scenario, for example, there may be mitigating barriers, so emergency response, or operational mitigating barriers such as emergency response, or you may have water deluge systems, water curtains to capture toxics, blast walls and firewalls to stop flammable outcomes from occurring, or at least mitigating their effect. Things like that. So Phast can help with these kinds of things as well, as can Safeti in a number of ways. Now, there are many tools for doing this job. it's kind of overwhelming that there's so many methods and techniques, but it's also very helpful because there are lots of useful ways to work on all the different aspects of major hazard management. There's just simple risk matrices that you can use for qualitative analysis of a very large range of hazards, and there's fault trees and event trees to try and work out how does loss of containment happen, how does loss of control happen, and once it has happened, how does that escalate to the end outcome, things like that. We have to consider human factors. You may have risk-based inspection programs on site to try and reduce the failure frequency, try and perform inspection on a risk basis, and focus your inspection efforts to try and predict and prevent failure from happening by replacing equipment and maintaining equipment based on its criticality. All manner of tools and techniques used. And here we have a way of organising these tools into some kind of logical structure. And this is the way I see things at the moment. What we have here is a pyramid of the level of detail, effectively, that you apply to a particular analysis. So you start off down at the bottom with qualitative analysis. And these are tools such as Bowtie, FMEA, fault tree and event trees, just thinking about the logical structure of how things can happen. Of course, probably the most common method here is HAZOP. It's kind of a good starting point for a risk analysis of any plant, is to go through line by line and consider all the deviations from normal conditions, what can cause them and what the result will be. And really here you're looking at the entire site, or a very large fraction of the site probably, at some point. So it's a large volume of work, and that's one reason why qualitative measures are applied at this stage, because you couldn't possibly do everything in detail. You couldn't put everything included in a HAZOP into a QRA, for example. You have to screen some things out just because there's too much volume to cover. Now, during HAZOP, for example, some other hazard methods such as Swift, you could, in theory, run fast and just do quick, fairly coarse consequence calculations, just to try and get some kind of ranking. So try and work out, is one spill worse than another spill? Things like that. Does the pool get bigger, or does the vapour cloud that results from a corrosion crack versus a line rupture, is it worse or not? Things like that. So you can do these simple checks during a HAZOP if you have time and experience. It's pretty straightforward. And moving up the pyramid to semi-quantitative, this is where you might be applying a little bit more rigour. And as I mentioned, during a HAZOP, you might take things a step further and start performing quick calculations with tools like Fast. You might also use lookup tables, so the Dow Fire and Explosion Index. Just fill out a form, assign some values to certain properties, how much of the substance, how toxic is the substance, and by the time you get to the bottom, you've got some kind of semi-quantitative measure of the severity of an outcome. You can also add criticality, so some kind of quantification of consequence and frequency into FMEA, and you end up with failure modes, effect, and criticality analysis. That's a useful measure. And you can also perform layers of protection analysis to try and think about the integrity of barriers that are in place for these accidents. Things like that. And as I mentioned, screening consequence and risk analyses. So not very detailed, but just kind of rough sessions of Fast and Safeti to try and compare one scenario versus another. And at this point, it's all about really building up your risk profile, trying to work out what's in the top right-hand corner of your risk matrix and trying to verify that by doing some more detailed analysis. And then we move up into the quantitative domain, and this is really the main area where Fast and Safeti fit, and it's where people are doing things like flammable risk analysis or quantified risk assessment. And just to compare quantitative with this higher peak in the tree here, detailed, it's quite interesting. So at the time you're doing quantitative analysis, we're thinking about all major accident hazards on a facility. We need to demonstrate to regulators or to stakeholders in our organisation that we've considered things that can go wrong, and we've got in place things to prevent them and mitigate them. So not everything can be covered here, of course. You know, you're still dealing with the entire site pretty much, but you've filtered out to just the major accident hazards on the site. Now there are some areas where you might have to go into more detail and use computational fluid dynamics. Another example is where you might have to perform experiments, because the generic traditional methods of performing risk analysis aren't appropriate for very detailed and unique, I've said here, novel major accident hazards. So very complex geometry, or maybe they're materials which traditionally we don't know too much about, so carbon dioxide, for example. And you'll see that experiments are being conducted today with hydrogen, CO2, so materials that are becoming more common in society and have to be part of the large volume analyses that we perform. So doing a QRA with CO2 that contains CO2 hazards, for example, can only really be done if we've got good validated models for CO2 releases. And this is something that DNV continuously work on. And an analogy for that is considering explosion overpressures or dispersion through complex geometry on plants and things. And it's not really possible to consider all major accident hazards using CFD. So for this reason, a number of people in industry got together and performed this project called Guidelines for the Application of the Multi-Energy Model, second project. And what it did, it ran lots and lots of CFD runs to come up with a parameter-based method for working out the overpressures developed from dispersion of flammable materials that are ignited within complex geometry. So rather than considering the very large number of variables that you do when performing CFD, you can instead just use several tuned parameters to come up with overpressures and explosion results which can be used for QRA. And it means that it makes the analysis realistic, and you can perform your studies in a realistic amount of time with a reasonable amount of resource.
We'll just have a quick introduction to Fast 7, and I'll try and give you a run through of the software briefly, and also kind of point out where we see this fits and how it can help in your job of managing major accident hazards. So just a little bit of background to give Fast 7 some context, just a little bit about how the software is structured and how it works. So here, very, very simply, there's linked models inside Fast that do lots of calculations for the things you need to investigate when managing major accident hazards. So we start off with discharge calculations. So very simply, how do you turn your process conditions through the description of an accidental release scenario into discharge terms? So if you've got a line rupture, given the material properties and the pressure and temperature of your process, how does that line rupture release material into the atmosphere? Or if you have a small corrosion crack, how does a small, several millimeter corrosion crack spray material out into the atmosphere? And those discharge terms are linked to dispersion calculations. So how does that liquid, or how does that flashing liquid, or how does that gas go out into the atmosphere, and then how does it behave when it's out in the atmosphere? And Fast can work this out. So you'll have some material going out to atmosphere, maybe the material is condensing as the vapor evaporates, takes the heat away from the liquid, it will get colder, droplets will form, and it may rain out on the ground. So there are some other model boxes we could link to here, but I wanted to keep it nice and simple. But the dispersion box here can link to a pool box. So you'll have a pool will form on the ground from this material raining out, and the pool will spread, it will warm up and start evaporating again. So the vapor from the cloud will get, from the pool will get added back to the cloud. So you have this sophisticated modeling, and it's all automated. Then there are a number of effect models, so hazardous effect models, hazardous outcome models, I guess I should call them. So looking at toxic impact. So if you have some gas traveling through the atmosphere, it's either vaporized from a pool or it was a gas release to begin with. What is the concentration and the exposure time at different locations downwind? So Fast can work out what's the dose experienced by this person. And then by using certain parameters that are stored in the material library system, we can convert that into a probability of death. So, 100 ppm of ammonia for 5 minutes has a different effect than 100 ppm of chlorine for 5 minutes. And there's a system in Fast there that will work that out and tell you what the impact is. And then we have lots of radiation calculations for different types of fires. So during discharge, for example, if you get immediate ignition, then the vapor fraction, or if it's a gas, it can burn and you'll get a jet fire. So we have a model that will work out what's the properties of the jet fire. How big is it? What's its angle? What's its burn rate? And then we have radiation models that will work out, given that jet flame, what's the incident radiation at distances away from the flame, things like that. We have similar radiation models for fireballs and also pool fires. If the dispersion modeling is worked out that a pool lands on the ground, it can be ignited and you can look at the effects of a pool fire. And then there's a number of explosion models as well. To look at multi-energy and Baker-Strelo, and also there's a TNT explosion model in there as well. So you can perform at distance steps downwind. The dispersion model knows the flammable mass in the atmosphere. You can ignite it and work out what's the distance to overpressure or impulse or pulse duration away from that ignition location. So a comprehensive suite of models, which I think there's 5 consecutive days of training you can sit on to learn about the details of all this modelling. So of course this is just a very brief introduction, and this may raise more questions than it answers. But here's an overview, and really the key message here is that Fast has this linked model approach, where you put in the kind of basic inputs: material, pressure, temperature, you describe your release scenario, and you can click run, and all of the calculations will be carried out. It's quick, easy, saves you time, and provides validated, reliable results that are consistent across your organization. And yeah, that's it really. Now, something worth mentioning, just kind of bear in mind, that of course providing you with a black box calculation tool wouldn't actually be that helpful. Most of the time it is, if you're happy with the modeling and you're happy with the results, but sometimes you want to do something a bit more detailed, or you want to check things step by step. And actually all of these models are separate, and you can start at different stages. So rather than having Fast calculate your source term, you can describe the source term yourself. So it might be a novel problem, or it might be something where you want to limit the release duration. For example, if you had emergency shutdown, you can start here. You can provide inputs manually to the dispersion model. And the same process applies to the flammable models and the explosion models. You can give a flame description, or you can have it just work out a flame size for you based on some basic inputs. Or you can give a flammable mass and say, do an explosion at this location and show me what it looks like on a map. So they are all linked, but they're also available independently should you need that as well, which is quite handy. So just on the next slide here, what we've got is just a kind of a busy slide just to indicate the extent of the capabilities, because that previous slide by no means does justice to the kind of rigor that the calculations actually have. So even if we look at just the dispersion model, there's different ways of handling different kinds of clouds, and it's the kind of thing that just a simple kind of spreadsheet tool, or like the Aloha method of Gaussian plume dispersion, you need more detail than that. And a cloud that doesn't touch down, or it does touch down but its centerline doesn't, compared to, you see here, compared to this third one down, it touches down and its centerline does touch the ground. They all behave very differently, and the entrainment factors and the momentum of the cloud are very different depending on how it behaves. And then at the bottom here we have a plume lifting off, a zero momentum plume lifting up off a pool, traveling along at wind speed. So, and that isn't the complete extent of all of the different types of pathways through the cloud modeling that you can have. So really the key message is that Fast works all this out for you, and it's validated against extensive experimental data, and all of that verification and validation work is published and provided with Fast. And of course the work is continuous, and you'll see us at conferences showing our latest results. So I'll give you a Fast 7 demo. I'll just take a moment to check that there aren't 100 hands in the air. Still 3 hands up in Russia. Now, if anybody is struggling with this presentation, if I'm going too fast, or if I've said anything that raises an important question, I'll give my email address at the end, and feel free to send me an email, and I'll try and clarify some things, or we can have a call. I can see there's a chap at GL has raised his hand as well. I must apologise. I think you guys don't have the ability to chat. I'm just trying to work out where that function is. So you've got your hands up very politely, but you're not able to ask a question. I might just ask one of my colleagues to help out while I carry on with the presentation, and we'll try and get your questions from the various people with their hands up. All right, so a demo of Fast version 7. Now, before I start this, I'll just mention that we have, at the topmost of the hierarchy, we have this QRA software called Safeti. And that does consequence modeling, and it takes account of frequency aspects of your QRA, and it combines them both. So that provides us with actually an isolated consequence modeling tool. So if you run this software looking at just the consequence aspects of the tool, then you've got Fast. So what I'm showing you now is Fast version 7. So they're both, Fast and Safeti are the same piece of software, but of course there's a development life cycle. We're in the process of upgrading the platform from version 6 point something to version 7, and during that development path, we build the software up, and the first thing that's ready is the consequence engine, Fast. So Fast 7 is ready, and it's here, and I'm going to demonstrate it. But I'm going to be showing you Safeti 6.7. So it's the older architecture version. And then, of course, at the moment, our developers are very busy building Safeti 7 as well. So that will be, it's an extension of Fast 7. That's the development path, and hopefully that excuses any confusion about the difference in the user interfaces. I have Fast 7 open here. Here it is. Now, as we're using webinar software, I'll try and do this nice and slowly because your screens may not update terribly rapidly. So the general layout of the software in Fast 7 here is a study tree on the left, and this is where all of our failure scenarios are entered. And you can see it's all organized by equipment. So here we have a pressure vessel called North Propane Tank. And this propane tank is a pressurized tank of propane that can suffer various types of release scenario. So you can see here I've got a catastrophic rupture, and then I have 3 leaks, a small, a medium, and a large leak. And there's lots of other types of scenarios you could put under there as well. So relief valves, ruptures of connected pipework. If this was an atmospheric storage tank, you could look at venting from the tank while the vessel was being filled, things like this. So, just from what I'm saying there, you can see catastrophic ruptures, major accident hazard with a high consequence and a low frequency, venting from vapor space, that's a kind of hazardous area classification problem, that kind of thing. And that's a low consequence, high frequency event, that kind of thing. So, what I'll just show you, I'll just open up the map. So there's a GIS system here, and if I open it up, that was surprisingly quick. You can see here's my 3 pieces of equipment on the map. I'll just zoom. You can see that's where they are. Well, 1, 2, 3. A nice simple example. But of course, looking at that plant, there would actually be a large number of pieces of equipment all over the site, and that's really the key thing. If you think back to the pyramid that I showed. There's a large number of scenarios that you have to consider, and if you're considering all the major accident hazards across your entire site, then you have to consider a lot of cases, and all of the cases across your site can be seen easily on the map. But of course, you can't consider everything. Not everything that shows up in a HAZOP will be included here. You got to filter out some things. But you can deal with a very large number of cases here, and lots of different scenarios for all of your different equipment. Now, if I just open up some of the results that I've got ready in advance here. So we've got 3 propane tanks on my map, and the North propane tank is of course the one up here in the north. And there's a number of failure scenarios. If I just have a look at the medium leak results. So first of all, well, before I do that, I'm jumping ahead of myself. Let's have a look at the inputs. So this is the kind of inputs you would use. If I double-click the piece of equipment, what you can see is a dialog box opens up, and there's specification of the material, propane, the inventory, we've got 100 tons in there, and then you specify how you want the conditions to be input. So I'm saying this is a saturated storage tank, so you can see I'm going to specify the temperature and then tell Fast work out what the pressure is based on it being at its bubble point. So I'm somewhere nice here, my tank's at 20 degrees C, ambient conditions, and that means today the tank is at 7 bar, 7.362 bar gauge. Now, because this is a saturated storage tank, I can release from the vapor space at the top. So if I'm releasing from a relief device on the top of the tank, I'll be releasing vapor. If it's a pipe rupture at the bottom of the tank, a kind of phase-on kind of accident, then I might be releasing liquid, and you've got that choice here of what it is you want to release. So you can see, for a piece of equipment, you'd have a whole spectrum of accidental releases that represent different kinds of failure. So that's the equipment itself. And then if I go down into a release scenario, I'll go down into this medium leak, for example. I just put in some very basic inputs. So a leak, all I need to describe is what's the hole size. You can see I've got a 1-inch leak, a 25mm leak, and then where is the release. So it's now, as I mentioned on the slide, this is really just the first half of risk analysis. You've put all your inputs and you've got your risk measure, but it's about, the next step is about understanding what are the risk contributors, and then carrying on from that, you would start thinking about mitigation measures. So what can you do to change your site, or how can you minimize those risks? So there's 2 very important tools for this. There's actually 3 very important tools for this, but I'll start with the initial ones. So here, if I look at my risk contours, you know that I've got some problems here on my site. I've got high risks going off site, hitting some population even in this location. But at the moment, I'm just doing a study and I'm looking at risks on site. Now, a very important tool here on the risk tab to help me understand these risks are risk ranking points. So you can see I've got a folder here called risk ranking points, and it's a key thing in any analysis, because you can't just produce risk contours and consider your job done. You have to consider the risk contributors. So as a result, I've put a risk ranking point at the warehouse and one at the control room, just in this simple example. Now, in reality, in a big comprehensive study, you'd put one at the nearest population, in muster areas, near expensive pieces of equipment, all manner of things. And we've kept this nice and simple. I'll just zoom in on that. In fact, if I hit Control and hit F4 on my keyboard, it will launch the map and show me where that is. So we saw the control room population block. I have on the map here a small blue dot. It's going to zoom in on it. There it is. A small blue dot at the control room. There we go. Hopefully you can see that. I've zoomed right in. There's my population block in a building, and there's a small blue dot. And that blue dot is really pivotal in understanding the risk contributors. So if I go to the Run Rows tab, go to View, Individual Risk Ranking Reports. I'm going to analyze my risk contour results, my individual risk. So I click on that, and I get some options. How do I want this individual risk ranking report to be displayed? And I'll just choose all the defaults, click OK. So it generates a report for me, and we'll see that this crystal report opens up. I'm just going to make it full screen. Just give that a moment so your screens can catch up. And I will scroll down a little bit. And what we've got here is a key tool in understanding your risks. So at the control room, which has this geometry, this location on the map, the blue dot we looked at, that's a risk ranking point called control room. You can call it whatever you like. These are the risk contributors. So these are the failure cases that hit that control room. So the scenario large leak, so south propane leak, large, contributes 42% of the risk. So the risk contribution is 3.1 times 10 to the minus 5, which if you sum all of the risk at that point and divide by this, that's 42% of the risk. So straight away, even on the first line, you know that if you've got a problem at the control room, it's kind of common sense. The south propane tank is the nearest to the control room. It's going to cause the biggest, largest amount of risk because it's the closest hazard. The effects will be greater close by. So looking down the list, what we've got next is the middle propane large leak. And it's surprising. So it's not the medium leak. It's not the larger, less frequent corrosion crack at the control room, and that's producing 24% of the risk. It's up at the middle propane leak large. It's not the medium of the south propane tank. And there's these kind of interwoven complexities that you can't work out in your mind really, even though you're very familiar with all the inputs and you may have done detailed review of the consequence results. It's this interplay of factors that is quite informative. And then you can see you've got the south propane leak medium contributes 20%, 19.83. There you go. So you've got this risk ranking. So if you've got a problem at the control room, if you know you can't lose it in an emergency, or if it's very expensive, you want to protect those 20 people, then this is how you can focus your efforts. This list here, the percentage risk, which is these risk values normalized. There's another very powerful measure here, risk per outcome. So this is the average risk divided by the failure frequency. This is very interesting. So it's a consequence view of things. So this is what's the probability of death at the control room if this large leak happens. So it's not thinking about frequency. You can see it doesn't have units per year. It's when the event happens, what's my probability of death at the control room. It's a very useful measure for risk ranking, or for consequence ranking in this case. All right, so that's the individual risk ranking report. There's also a very similar report for the FN curves, but time's running on quite a lot, so I'll speed up a little bit. But the societal risk ranking report will give you a very similar measure. It will tell you which cases contribute to which fatalities. Now, if we had more time, or if you're interested in any follow-up, you can ask one of our sales guys or our tech support team, if you're an existing customer, about how to dig down even deeper, because there's lots of tools here for digging down deeper. Because actually, though some of you may have spotted here, listing the release cases is not enough. That's the center of the bow tie, right? You've still got an event tree following on from a large leak. So of all of this risk, what's causing the hazard? Is it what's causing the outcome? Is it a fireball? Well, sorry, these are leaks. So is it the jet fire? Is it a delayed explosion? Things like that. So there's depending on the kind of release you've got lots of different end branches of event trees. If this was a material that was two-phase that formed a pool and a cloud, is it a flash fire, an explosion, a pool fire, the initial jet fire? And you don't know. So there's options you can tick, and there's a whole other kind of sophisticated risk reporting tool, which I'll get onto in a moment, which allows you to drill down even more. Because knowing that this particular tank is the main culprit is the first step. You need to dig down a little bit deeper further and find out which particular hazards have you got to mitigate against. If immediate ignition is your big risk contributor, then deal with your ignition sources. If vapor cloud explosions are, then make sure that you don't have congested regions playing around with the vapor cloud and causing impact at this location. Okay, so that's an overview of Safeti. So the kind of the process of adding additional inputs, ignition, population, failure frequency, weather probability. You just very simply, you run your calculations. It goes on from what Fast has already calculated and combines all of these risk measures. You can then look at individual risk and perform risk ranking. You can look at your FN curve and look at societal risk ranking as well. And that's very briefly an overview of Safeti. Okay, so the final thing I'm going to talk about is the Safeti 3D extension. So, of course, over the years, we're extending the software in lots of different ways. We're also reworking things we've got. We're validating models and improving the user interface and the reporting capabilities and things. But this particular extension, it's a chargeable extension that you can optionally add on to Safeti that does a couple of specific tasks, and I'll just mention what they are now. So the first big job it does is to perform congested explosion modeling. So the traditional method, the kind of purple book method of explosion modeling in QRA, is to just assume, very conservatively, a single explosion strength everywhere. So the only variance is the flammable mass, based on your dispersion results. So what happens when this flammable mass explodes with this strength? That's a traditional approach. But it's not good enough, really. And there's been lots of methods evolved to improve this technique. So, of course, you're doing a QRA, you're looking at lots of weather directions, lots of interactions of different flammable masses at different time steps during dispersion, and the clouds going in different directions and encountering different congested regions where explosions can happen if there's ignition. So there's thousands, if not tens of thousands of explosion scenarios that need to be considered. So this kind of alludes to what I was talking about before with this pyramid of detail. There's been methods developed which support the analysis of thousands and tens of thousands of explosion scenarios, but of course that it can't solve all the problems. You know, it's a generalized method that we've used here in Safeti, and sometimes you have to do CFD, right? So what we're looking at here is the multi-energy explosion curves, which correlates overpressure on the y-axis with distance on the x-axis. So this method consists of you somehow determining a blast strength from 1 to 10. So 10 is very, very congested. If you have a fixed amount of flammable mass and it's dispersed through a level 10 region of congestion, you'll get extremely high overpressures in the near field. If you have an unconfined area, something with a blast strength of 1 or 2, you get relatively low explosion strength in the near field. Process plants, typically complex process plants, are up around 6, 7, 8, 9, and 10. They're pretty high levels of explosion. Thankfully, they all converge in the far field, and as you move further away from the source, the results are pretty similar. So it's really in the near field, it's the destruction of the plant that's of concern, really. So that's the first job that Fast Risk does. Now I'll just go into Fast Risk and show you how this method works. So here in Fast Risk, standard Safeti can be extended with this 3D. I don't know if you can see down here on my status bar. The 3D obstructed region option is selected, so I have a license for that on this computer. With that selected, here on the map tab, I can place congested regions on the map. So if I close all those windows down over there and just open up my map will open up now, and there'll be some pink rectangles on the map which actually represent volumes, and they've been given certain attributes which specify their level of obstruction, right, which is their level of congestion and confinement, these two aspects of congested region. So the method that's been adopted in Fast, there's actually two. There's a Baker-Strelo tang, and there's the multi-energy, the TNO multi-energy method. So we saw some curves there on the slide. Those are the blast curves for the TNO multi-energy method. There's this very important project that was done called the Guideline for the Application of the Multi-Energy Method. It was actually conducted twice. There was a second project as well. So there's a project called GAMES, Guidelines for the Application of the Multi-Energy Model, second project. And we've adopted this method in Fast because traditionally in standard Safeti and Fast, you just pick a curve strength. But of course the obvious question is, which curve strength is it? So the GAMES method came up with this parameterized method for defining obstruction strength. So here I've got this OSR1 two-story main building. And if I press F4, there it is on the map. You can see it's been centered and selected on the map to show me where it is. If I double click it, I just have to put in some basic inputs. So when the explosion blast wave expands, how can it expand? I've chosen 3D. So it's not between two concrete slabs, for example. It can expand in all directions. What's the volume blockage ratio? i.e., how much is free space and how much is made up of pipes and vessels and, basically volume where the cloud can't sit. And then to describe the congestion, I have to give the typical diameter of the obstructions. So is it lots of very thin pipes, or is it drums, or is it several big vessels? Things like that. I could put that in as a surface area sum. So what's the surface area to volume ratio? Because a volume with tiny little pipes in it will have a very high surface area to volume ratio. Big drums won't. And then what's the flame path length? So it can calculate that for you based on the shape you drew on the map, or you can specify it yourself. And that's it. So using that method, if you read the GAMES report, you can see that those inputs are used to pick a blast strength from 1 to 10. It's that straightforward. So what Fast Risk will do is it will consider, here you go, so here's a blue dot on the map. You can see there, that's if I just click on it, we'll see what that is. That's a collection of south propane tank releases. So given different wind directions, blowing to the north and to the northeast, the cloud will disperse in different directions. It may encounter an ignition source and also be in an obstructed region at the same time. If it is, you'll get an explosion. But of course, you don't always have 100% probability of ignition. So you do one time step and you blow up and you see what the results are. And then you think about the parallel universe where that didn't happen. So you go on to the next time step and you blow up again. And is that worse? Now, the next time step, of course, you'll have had more entrainment. So you've got a lower concentration, a lower flammable mass, but you might now be nearer to the control room. So which one is the worst hazard? And Fast Risk conducts all of these calculations. It's quite good, in my opinion. So that's the first aspect of things. You put your congested regions on the map and you use the games method to assist you in assigning blast strengths to the various congested regions. Okay, that's the first part of things. Now, the second kind of major enhancement that comes along with this extension is the aspect of location-specific vulnerability. So if I just move on to the next slide here, right, you've got two examples of building types. The one on the left is this very weak, flimsy kind of porter cabin, the kind of thing that put there temporarily for people to work in during maintenance and things like that. On the right, we have a generic image of a blast-proof room grabbed off Google. So I'm not quite sure what its blast strength is, but it's protected. It's a thick steel plate, it's got thick glass windows, and it's tested and certified against certain blast overpressures and impulses. And if those people are on your site in that building, if you're, for example, in the US and you're following the API recommended practices 752 and 753, you have to perform occupied building analysis. And depending on which of these buildings you choose to use, the occupants of the building will have different levels of protection. If I just go on to the next slide, you can see there's organizations like the Chemical Industry Association have produced correlations between lethality, there on the y-axis, and overpressure on the x-axis. So these CIA guidelines show you different levels of protection from different kinds of buildings. So hardened structure, special construction with no windows, offers you very high levels of protection up to high overpressures. So it's the blue curve. You don't have a very high lethality until you get very high overpressures. Whereas a porter cabin, which is a brand of temporary building, temporary kind of timber-framed construction, has a very low resistance to overpressure. So you've got a high probability of death inside there if you experience these different overpressures. And this vulnerability modeling is also available in Safeti with the explosion extension. So if I go into, it's called here, Safeti 6.7 workshop, right? So here I am in Safeti, and on the map tab, I've defined several building types, and these are actually just the CIA building types that we saw in that graph there. They're slightly out of date, I think. They're from 1998. There's a more recent set. So we've got the hardened special construction with no windows, and the values of resistance to explosion have been put here in this table. So those are the values from that table. So what's the overpressure level, and what's the probability of death? And we've basically built those curves up in a table. And then certain population members have been put inside that building. So there's a control room building that population have been put inside. And we can see that here. So we'll go on to the risk tab and scroll down. The control room people, we go to the geometry, are inside this hardened special construction, no windows. I might have several of those building types around the site, and I might put different populations in them. So there might be 10 people in one of them in one location, 7 of them in another location somewhere else. So using this, we can perform vulnerability-specific risk modeling, and it's very important for occupied building analysis. So you can imagine, if I just fire up my FN curve, you can imagine that if I chose to put number of people I've worked out are going to be exposed to particular blast overpressures for my risk ranking drill downs, I could choose to put those people in hardened buildings, or I can invest in protection. And you'll see this FN curve come down because those people will no longer be subject to lethality because of the protection that the building offers. And that's the idea. So it's just extending Safeti a little bit more. You put in your congested regions, You define vulnerability types. They're actually called building types, but they could be any kind of vulnerability, really. It could be people trained in emergency response. These certain people could have a level of protection because of that. And then your results, because it's the extent of the results are quite varied and sophisticated, we actually had to extend Safeti with this extended risk reporting tool. And that's the last thing I'm going to show you before we switch over to questions. So here's the extended risk reporting tool, and it opens up in a new window. It takes up so much space that it deserves its own little side application, and it's a really nice tool. It sits on top of a database which pivots through all of the data and provides you with cross-referencing and analysing all of these risk results. So it's very similar to what we did with the risk ranking report and the societal risk report, where you can drill down into your results. So in much the same way that there was a risk ranking point at the control room, and I saw that the south propane tank was contributing the most risk, I can equally now get results of what overpressures can impact that control room. So I've set up a filter set, it's called here, and I've said, show me the warehouse and the control rooms. And I want to include all of the different hazards that impact them. But I can produce individual risk ranking reports, just like I could in standard Safeti, but I can also in here produce curves of side-on overpressure exceedance. So if I just click on that button there, so this is kind of like an FN curve, but it's showing us all of the different explosions that can hit the control room in the warehouse. So the cloud's going to drift off through space, it's going to ignite at different time steps, and the different blasts are going to be hitting the control room of the warehouse. And this shows me the frequency with which I can expect different levels of overpressure. So overpressure there on the x-axis, frequency of exceeding the overpressure on the y-axis. So it's a cumulative plot. And you can see I've got 1 in 100,000 chance of getting up to 0.1 bar, and then I get a bit of a drop-off at the warehouse, and then I've got a fairly low probability of getting a fairly low frequency of getting these higher overpressures, which is key information really. So you would use this from a risk perspective. You could say, how much frequency are you willing to tolerate? 1 in a million chance of getting 100 millibar, or 1 in 100,000, and you can decide where your building is. You can maybe move your control room outside of that blast zone if you're not willing, if you don't have that appetite for risk. You could just look at the overpressure as a plot. So here I've set up a vulnerability type that just shows me 0.3 bar overpressure. So if I click on the risk contour results now, I can get a plot of what's the frequency of getting 0.3 bar overpressure on my site. So it's using the same kind of algorithms as individual risk contours. But I've said, don't show me all of the probability of death summed together for all of the effects. Only show me where 0.3 bar overpressure can occur. So the GIS should open up. Here it comes. And then it should be plotting these contours for me. And I'll get risk outputs of the frequency of experiencing this 0.3 bar overpressure. So I just need to zoom in on the site a little bit. Of course, it doesn't look that far, 0.3 bar overpressure. I'll just scroll down in the legend. I'll drag the aerial photo up in the stack so I'll get a bit more detail. There you can see I've got a pretty high frequency. There you go, the orange line, which in the legend is 1 in a million. But I'm well inside the 1 in a million frequency line for experiencing 0.3 bar overpressure. But you can see the warehouse, the blue dot for the warehouse is outside that line. So two different ways of viewing the overpressure results at that location. I could do the same thing for toxic concentration. I could do the same kind of plot for radiation as well. So it's a particular level of radiation or radiation dose. So I could see, where do I get 4 kilowatts of radiation from any kind of fire, from any release source and any ignition on my entire site. It's a very useful view of the results. So that brings me to the end of the demonstrations. I overran a bit slightly, and I apologise for starting a little late. So we will open up for questions, if you're willing. Okay, so I'll ask my colleague Steve to fence those questions. If you could, I'm just going to look at the attendee list. If you could raise your hand, I will unmute you so that all of the other delegates, all the other attendees can hear you as well. If anybody has any questions, click on the raise your hand function in this GoToWebinar tool. Okay, so no hands have gone up just yet. Hopefully I haven't been speaking to empty space for an hour. Lots of questions. Okay, so I've got Per Filskov. Okay, I'm just going to unmute you.
Can you hear me now?
I can hear you now, yeah.
Okay, hopefully everyone else can as well. Well, I gave you a question on the chat some time ago, but you partly answered it later. That was about the building vulnerabilities, because I saw when you demonstrated how you could see the individual risk for people in a control room, you chose outdoor vulnerability. So my question was, if you were then choosing indoor vulnerability, could you then choose different building types? Because there's a big difference between sitting in a blast-proof control room or a porter cabin.
Exactly.
But later you then explained that if you're using the extension, then you would actually have this possibility of choosing different building types. But in the more general Fast law of Safeti, can you also choose there between different building types, or is it just a general indoor vulnerability, and then you have to go to the more specialized explosion version to get the different building types?
Yeah, you've answered that yourself. It's standard indoor, outdoor, and then there's the specific building vulnerabilities are only available in this extension.
Okay, thank you.
Okay, thank you. I'm going to mute you if that's okay.
Yeah, that's fine.
Yeah, great. All right, on to the next question from Ali Silva. Hi, Ali. Can you hear me?
Yeah, I can hear you. Can you hear me?
Yes.
Oh, great. Then. My question is related to the buildings as well. Just want to know if the population assigned for a building is it distributed across the area assigned for the building, or is it a point population there? And how is it treated in the constraints and risk assessment if it is a point or an area population?
Sorry, Ali, I'm struggling to hear the question.
Oh, sorry. Is it better now?
It's a little bit echoey.
Okay, let's try once more.
Yeah.
My question is associated to how population is assigned to buildings. Is it an area, it becomes an area population, or is the population distributed across the area for associated building, or is it a point population?
Yeah, there's several ways to enter population. So if you're using the extension, then you put buildings on the map and you put the people in those buildings, so they have a very specific location. And alternatively, there are lots of other population mechanisms as well. So if you're, as Per Filskov asked, there's the traditional method of generic vulnerability and then building specific vulnerability. So you can see here the 4 population types. So in the extension, you put them in a building and they have specific vulnerability. For everybody else, you can use points, rectangles, and polygons. So you put these shapes on the map, and then you say how many people there are, and what fraction are indoors, and what fraction are outdoors. And the indoor and outdoor fractions use these very generic indoor and outdoor vulnerabilities, these purple book indoor-outdoor vulnerability probits.
I see. When you assign a population for a building, as you just showed, is it considered point population or an area population?
You have both options.
For buildings?
For buildings, yeah, points and areas too, yeah. Yeah, so you've got...
They are points then.
Yeah, you've got, oh, hang on. Yeah, no, it's areas. Yeah, and when there's a loss, the entire building is lost. So if if an impact zone hits one corner of a building, everybody in the building's dead. So the idea is that the building hits the person as well.
Okay, so if a fraction of the building is exposed, the whole population is considered.
That's right.
Okay,
yeah.
Cool. Thanks a lot.
Okay, thanks, Ali. Okay, now next hand that is up, okay, is from somebody who is Sadala. But it looks like so Kranti Kumar Sadala has put his hand up, but there is no audio device plugged into your computer, this says. So I'll just give you a minute. There you go. Now you're on. Okay. So Kranti Kumar, there you go. You've now got voice.
You are muted.
Hello. Can you hear me?
No.
Haha. Maybe you can. All right. I'll move on to the next question while I get some microphone sorted. So we have another hand up from... Okay, that's all the hands up for now. I think Vikas, you had your hand up, but you put it back down again very politely. Turi, you've still got your hand up, but I'm guessing I can talk to you after the meeting. Okay, so we might try Kumar. Okay, I'll give you one more try, Kumar. Oh, no audio device, it says. Okay. All right, well, that takes us to 11:30. So I'm just going to pass back to my colleague, Steve, who's going to close the meeting.
Okay, thank you very much for listening in, and I hope it was well spent time. Please let us know by email if you have any questions or would like some more information from us. Or if you would like to test the software, I can provide you with a test version. You can also visit our web pages, www.dnvsoftware.com. There you will find additional information, of course, and information about training and so on. And also some videos and other nice stuff to look at. So we hope to be in touch with you soon again, and thank you very much for joining. Wish you a nice weekend soon. Okay, bye.